Okay, everybody, welcome. We are going to be taking a look at a new rule today called the chain rule. So I don't know if anybody knows Mr. T, who pities the fool that doesn't know the chain rule. So we're going to take a look at this really important rule. It's kind of along the lines of product and quotient rule. And it is a rule that is going to be used almost practically all the time from for our derivatives from here on out. And you'll see why in a second when we start to take a look. As always, just make sure that you got your notebook ready. 3-6 chain rule. You will need your foldable because we're going to have a formula or two to write down. If we run out of room in our foldable, then we will make sure that we get a new one. So at least write down the formulas that we're going to get here in a second. So we've got a bunch of shortcuts so far. We've got the power rule and we've got our trig, 6 trig derivatives at this point. But there's other functions that are going to be a little bit more involved. So for instance, if at this point I would like to take the derivative of x plus 2 squared, well, I can't perform the power rule on this because it's not just a single x to a power, it's a function to a power. So what would I have to do here? Well, yeah, I'd have to expand it out. So expand this out and we would have y equals, use a pen here. So I'd have y equals x squared plus, I believe, 4x. Yeah, and if I take x plus 2 times x plus 2 plus 4. So, and if I do that at this point, then I should be able to take its derivative, and the derivative then is 2x plus 4. Well, that's nice and easy, and we can do that, and we have things we've seen that already, but what about this? Well, I'm not going to want to expand this out. I can use Pascal's triangle and do some binomial expansion, and that's actually kind of fun, but that's pretty tedious. So I've got to figure out a way to take derivatives when I've got a function to a power, and that's got to be a better way than doing all of this explicit form. Okay, so let's consider an example here. Let's take a super simple situation and break it into a situation that looks like a function inside of another function. Okay, so we're going to take 6x minus 10. All right, so at this point, cat's out of the bag. I already know the derivative is going to be 6. But let's look at this a little bit differently. So I'm going to factor out a 2. So if I factor out a 2, then it's 2 times this other equation. So now I'm getting more along the lines of like a multiple equations involved in here instead of just single variables. And I'm going to let u, I'm going to define the function 3x minus 5 to be the function u. And you might want to set up your paper as I'm doing it here too. Again, remember, you can always pause and go back if I'm going fast. But if u is 3x minus 5, then I'm going to rewrite my expression, 2 times 3x minus 5, in terms of u. And so that would just be y equals 2 times u, 2u. So I've taken this equation, 6x minus 10, I've defined u to be 3x minus 5, and therefore then the function now is 2 times u. So if I substituted u back in, I would wind up getting my equation. So I'm just breaking apart what was once something simple. And we'll see why I'm doing this in a second. Let's see what happens. Well, first of all, the derivative dy dx, the derivative of y in terms of x, is 6. We already knew that. All right, but let's go and take the derivative of the other terms. The derivative of y equals 2u, well, first of all, what's the notation going to be? dy du is going to be 2. So that's no big deal. It's just a little linear term. And now, if I take the derivative of the last term, so that's going to be du dx, and du dx is simply just 3. Huh. Well, what do you think I got to do with these two derivatives that I just found to get the actual derivative? Well, yeah, I got to multiply them together. So 2 times 3 gives me 6, but what does that mean that's happening? Well, then that means that dy dx must be equal to dy du times du dx. Well, does that make sense? Even just look at the notation. What would happen to the du's? The du's themselves would cancel out, giving me dy dx. So if I break a function down into two functions, one composed of another, and like a chain, We'll see more why it's a chain down the road. But then I can just take the derivative of y function in terms of u times the derivative of the u function in terms of x, and I would get dy dx. That is the beginnings of our chain rule. We'll jot that down in a minute. Okay, let's do another one. Okay, so take a function that we clearly already know what its derivative is going to be. We know its derivative is going to be 18x plus 6. But I want to rewrite it in such a way so that I can look at it as a function inside of another function. So what I have in this case, if I factored it, it's going to be 3x plus 1, the quantity squared. So what am I going to pick for the u function? What's the function that's kind of inside here? Yeah, that's 3x plus 1. And then if u equals 3x plus 1, I can now rewrite the whole equation as u squared. So y equals u squared. All right, so at this point, again, I can take the derivative. I already know the answer is going to be 18x plus 6. But if I look at the way that I decompose this function and take the derivative of these individual equations, dy du is 2u, du dx, that's just going to be 3. Oh, before I even do that, let's substitute u in. So u itself has been defined to be 3x plus 1. So there's me putting that in. And I'll even go as far as simplifying it. So there we go. There's dy du in terms of x, because ultimately we have derivatives in terms of x. So now we can go over and take the derivative of du dx. It's just simply 3. And from what we saw last time, dy dx was just simply the product of these two. So I multiply them together, and sure enough, I get the same answer. I get 18x plus 6 if I distribute that 3 through there. So yeah, dy dx equals dy du times du dx. Now, typically, we're not going to take simple equations and make them into this form. We're usually going to see them in this form, which we'll see here in a second. So there is my chain rule. This is called the chain rule. And at this point, we could, on our foldable, put on the outside chain rule. I would put on the outside chain rule, and then dy dx equals, and then on the inside, I would put dy du times du dx. All right. So at this point, let's now take a look at an example. So I want to take the derivative of y equals, going back to that equation that I did before. I'm going to go back and now take the derivative of that. So I'm going to come in here, give me 1 second. All right. All right, so y equals x squared plus 2 to the 6th. So now I want to, first thing I got to figure out is what am I picking for u? So I'm going to let u be x plus 2. That function sitting on the inside. So therefore, my function can be rewritten as what in terms of u? And that's going to be u to the 6th. All right, so now underneath each of these, I'm going to take dy du, derivative of y in terms of u. It's going to be 6u to the 5th. And then I'm going to take du dx. And what is du dx? Oh, du dx is just, looks like it's just 1. So now our chain rule is saying that dy dx is dy du times du dx. And in that case, dy du is 6u to the 5th. Du dx is 1. Now, do I leave my answer like that? No, because I need the derivative to be in terms of x, not u. So can I write u in terms of x? Well, yeah, I already did it up earlier. So I can now say it's going to be 6x plus 2 to the 5th times 1. So one would say, well, can't I just use the power rule, and aren't I just taking the power down and subtracting by 1? But yeah, but what's also happening is then I was taking the derivative of the x plus 2. That's where that 1 came from. So there is a second step of me taking the derivative of what's on the inside. So let's try another one here. All right, if you want to pause me now and try it on your own, pick a u, rewrite the function in terms of u, and take your derivatives, and then see what you get. And then turn the video back on. Well, hopefully we see that u is this function on the inside. It's literally on the inside of the radical. And that means then my whole original function is the square root of u. So something to think about in terms of picking u values, you want to pick a u value that makes your original function easy to differentiate. If you pick a u value and you still can't take the derivative of the y equation, well, then you picked the wrong value for u. And that might happen. We'll talk about that. All right, let's go and get our derivatives. dy du. So a little power rule on that one. And du dx. And dy dx is a product of the two. So 1/2 u to the negative 1/2 times 6x squared plus 2x plus 1. But again, I don't like that because I've got a mixes of x's and u's, so I need to rewrite u in terms of x. Do I have that? Yeah, there's my u in terms of x. So dy dx is 1/2 u to the negative 1/2 times du. There is my derivative of the square root. You could go on to simplify this. Simplify this just a little bit more. dy dx. The negative exponent, that's going to go to the denominator, and it's a square root. So I think in the end, I'll have this up in the numerator. I have the little 2 from the fraction of 1/2, and then from the negative 1/2 power, I get the square root in the denominator. All right, let's try another one. Again, pause me, try it, pick a u, take the derivative, give me the full derivative in terms of x, not in terms of u. So I'm already getting in the habit of now starting to write the y equals u to the 3/2, so therefore u must be x to the 4th minus 1. So if you haven't noticed by now, this is why I'm really big on making sure you're using the proper notation. dy du, du dx. They're very specific about what is the variable of the function and what is the variable that you're differentiating in terms of. So dy dx equals 3/2. And I'm going to actually go ahead and throw the u in. We've done this a couple times. So now let me put u to the 1/2 times 4x cubed. And I'm done. Now, if you want to simplify it, again, some answers might need to be simplified. I've got constants of 3/2 and 4. Those are my constants, so I got 12/2, so it looks like I'm getting 6x cubed with this extra x to the 4th minus 1. So you might see some of our derivatives being simplified. If it's not multiple choice, so you don't have to do anything or match an answer, well, then just leave it in unsimplified form. That's totally fine with me. So another form of the derivative in terms of chain rule is f of g of x. This is really what chain rule is all about. It's the fact that functions are inside of other functions. So functions are inside of other functions. So what would happen if I took the derivative of f of g of x? Oops. F of g of x, well, what we were doing was taking the derivative of the outside function in terms of u, g of x being my u, times the derivative of the inside function. So dy or d dx of f of g of x is the derivative of the outside function in terms of the inside function times the derivative of the inside function. This I would maybe put on my foldable. This on the outside, d dx of f of g of x. and this goes on the inside. This is another form of the chain rule. So in this case, for this problem, so I've got a function f of x and a function g of x. So f of g of x is the sine of x squared minus 4. So what I want to do in the notation that got messed up over here is remember f of g of x. I don't know if you've seen that that's sometimes written as fog notation. So I want to take the derivative of f of g of x, or in other words, take the derivative of f of g of x at x equals 2. So let's write down what we know. d dx of f of g of x equals f prime g of x times g prime of x. All right, so what do we have? The derivative of the f function, well, derivative of the f function is the cosine function. But it's the cosine function in terms of the g function. So I'm going to do cosine of x squared minus 4 times the derivative of the g function. Well, what's the derivative of the g function? That's easy. That's just 2x. But what I want is I want the derivative of f of g of x at x equals 2. So I want the cosine of 2 squared minus 4 times 2 times 2. So that's the cosine of 0, which is just 1, and 1 times 2 is 2. So in the end, I get 2. Is there a second way that I can kind of look at this problem? Yeah, let's just look at this one other way. Since I was actually taking the derivative at 2, so really what I was looking for, yeah, I'll do this, is I want the derivative of f of g of x at x equals 2 is going to be f prime g of 2 times g prime of 2. Well, go up to the original. What is g of 2? G of 2 is 2 squared minus 2. That's 0. So now I need the derivative of f at 0. Well, what's the derivative of f? Well, that's cosine. So that's cosine of 0. The derivative of g at 2? Well, the derivative of g is 2x. So that's 2 times 2. 2 times 2. Oh, was this answer 4? Oops. That's my mess up from before. Sorry. Going back to I couldn't even read my handwriting up here. So back of this last problem, this should have been 2 times 2 is 4. Sorry if you were yelling at me that I got it wrong. But good thing I checked it. So now I have a second method of checking and I'm seeing that I'm okay. Here's what it's going to look like on the AP exam. So I've got a table of values for g, h, g prime, and h prime at 2 different values, at -2 and 3. So the question is asking, what is the derivative of g of h at x equals 2? So I don't know what these functions are, but I do know that the derivative of g of h of x, and we're going to say at x equals 2, is g prime h of 2 times h prime of 2. Derivative of the outside function in terms of the inside function times the derivative of the inside function. Well, let's start working it. What is h of 2? Oops, -2. That's my fault. I was looking up at the table. I don't have any 2 values. Yeah, I was at -2. So h of -2 is 3. So that's g prime of 3, h prime of -2. Now let's go and get derivative values. G prime of 3, well, that's 1. H prime of -2, that's -5. So I get -5. That would be my solution. I have no idea what the functions are, but I can figure out what the derivative is at -2 using a table of values. Very similar to what we just had done recently on a quiz. So to wrap up here, Common mistake that people make is not using the chain rule. So be careful. If you've got a function inside of another function, you can take the chain rule. But honestly, every single derivative we've ever done could be done through the chain rule. Even something as simple as x squared. So the derivative of the function of if we look at this, if I let u be x, the derivative would be derivative u squared is 2u times the derivative of x. Well, that just turns out to be 1. So every time I take a derivative, I could be taking the derivative of x squared is just 2x times the derivative of x, which is just 1, but I'm going to get 2x. So it's a little overkill if I'm going to do it with every single problem. I only need to do it with the problems that have compositions of functions. One function that's not just a single variable substituted into another function. All right, check online to see some practice problems. We are gonna practice these for a couple days now because this is everywhere. All right, good luck, guys.